Hi, my name is Muhammad Tariq, and in this lecture, we will discuss rotations. In last lecture, we discussed about AVL trees and why we use AVL trees. What was the problem with the binary search trees that we came up with the idea of AVL trees. And now we will continue our discussion on AVL trees and we will discuss about rotation. So let's quickly recap about AVL trees. Many algorithms exist for keeping binary search trees balanced. Adelson, Velsky, and Landis. See, these are the inventors of AVL trees, and this is also called height balance trees. Splay trees and other self-adjusting trees. We also have state trees. We will discuss them in our next lectures. We also have B trees. Okay, why AVL tree? Why we use AVL trees? So most of the BST is the short form of binary search tree. Most of the BST operations like search, max, min, insert, delete take O of h time, where h is the height of the binary search tree. So the ideal situation, these operations, search, minimum, maximum, insert and delete, these operations would take O of h time. So it's actually the log of n. The cost of these operations may become O of n for a skewed binary tree. Now, what was the skewed binary tree? In last lecture, I discussed with you, I showed you something like this. We have something like, right? I showed you a tree like this. So this is called skewed binary tree. Either on right hand side or on left hand side, we have like this. So this is the skewed binary tree. This is left skewed and this is right skewed. Okay. So these are called skewed binary trees. And these tree will result in O of n time. In the number of nodes we have, we will have to search and we will have to compare each node to get to the result. If we make sure that height of the tree remains log of n after every insertion and deletion, then we can guarantee an upper bound of log of n for all these operations. So this point is explaining that if we make sure that the height of the tree remains log of n, right? If we make sure that the height of the tree remains log of n, then all the operations that we discussed, like this search, maximum, minimum, insert, these operations will result in an upper bound of log of n. We can guarantee an upper bound of log of n. The height of an AVL tree is always log of n, where n is the number of nodes in the tree. Okay, now before moving further, let me draw a sample tree here. Let me draw a sample tree here. Let's make it 50, 40, 30, right? And let's keep it simple. So now let's try to calculate the balance factor of this tree. The balance factor of 30 would be 0, right? We discussed last time. There is no left subtree and neither we have right subtree. The balance factor of 40 will be 1 because on right hand side, on right subtree we have, sorry, on left hand side we have 1. The left subtree, the height of the left subtree is 1 and the height of the right subtree is 0. So 1 minus 0 is 1. Now what is the balance factor of 50? The height of the right subtree is 2 minus 0. There is nothing on the right hand side. We have the height of the left hand side, we have 2. The balance factor of this node, which is 50, it's 2. So the acceptable balance factors we know, which is 1, sorry, minus 1, 0, and 1. These are the three acceptable values, but we have something which is not acceptable, which is 2. So for make it an AVL tree, a balanced tree, we will have to apply rotation. Let's see how we can apply rotation. So to perform rotation, it is necessary to identify a specific node A, right? We will identify A whose balance factor is neither 0, is neither -1, 0 or 1, and which is the nearest ancestor to the inserted node on the path from the inserted node to the root. Now what does that mean? Now as you can see here, we have a, a tree with 3 nodes. Now we will have to mark a node with A, and that node should not be the one which has the balance factor of this acceptable range. So here we have 2. The 2 is acting as an A, right? So now we have identified the node which we will have to mark as an A. And because this is uh, how you mark A, because this does not contain the acceptable range of balance factor. It's contained 2 which is out of this range. Before applying rotations, we'll have to identify which type of rotation we will select on this tree. We have 4 types of rotation, right? We have 4 types of rotations: L rotation, R rotation, LR rotation, and RL rotation. So what is LL rotation? LL rotation says inserted node is in the left of the left subtree of node A. Now what is this? Let's look at this picture again. Sorry, we inserted 30, we inserted 40. So both these nodes are on the left side. Okay, both these nodes are on the left side of this tree. So on the left hand side of 50 we inserted 40, on the left hand side of 40 we inserted 30. So it is LL, right? Left and left. So we inserted a node on the we inserted 30 on the left hand side or on the left subtree of 50, right? Let's again read uh, the sentence. Inserted node is in the left of the left subtree of node A. So the node A, as we have identified, which is 50, this is the node A we have, and we have inserted 30 on the left hand side, on the left subtree of the inserted node, right? This is the left subtree of the inserted node, and we have inserted 30 on the left subtree of the inserted node. So now we've also identified that we'll have to apply LL rotation. In the same way, for RR, the case will be something very similar, and you must have guessed it by now that it is 60 and it is 70. So this is the RR case, because now we have inserted the node on the right hand side, of the right subtree of the node A. Now if we again calculate the balance factor, so it will be 0, this will be -1, this will be -2. So this node 50, is the candidate to be signaled as A, and 60 is on the left, is on the right hand side, and we have 70, which is the we have inserted this on the right subtree of the node A. So here we can apply our R rotation. Okay, now we also have LR and RL. For RL, we have something like 50, and on the right hand side we have 60. Okay, and then we have something like 51. Okay, so this is the case for RL. Balance factor is 0. Here the balance factor is 1. Okay, and here the balance factor is on the right hand side, and here the balance factor is 2, right? Because the height, we take the height into consideration, and this will be A, this will be A node. So here it's right hand side, and then it's left hand side. So the node we insert on the left side of the right subtree, right? The node we inserted on the left side, this is the left side of the right subtree. This is the right subtree. Okay, the 60 is actually the right subtree. And for the last case, we have 50, and then we have 40, and then we have something, we have 45. So this case, the balance factor of 45 is 0. The balance factor of 40 is minus 1, right? Why minus 1? Because we do not have anything on the left hand side. So it's 0 minus 1, right? It's 0. And on the right hand side, we have 1. So it's 0 minus 1. And for 50, it's, it's 2, right? So here, so this is the A. This is, you can mark as A because this contains a value which is neither 0, neither 1, and neither minus 1. And we have inserted a node on the left subtree, on the right of the left subtree. On the right, this is the right of the left subtree. This is the left subtree. So this is LR. This is LR. This case is LR. This is LR. This is RL. This is LL. And this is RR, right? Okay, we have seen all four cases. Now we will see how we can apply rotation and how we can turn these unbalanced trees into AVL trees and balanced trees. So to turn them into, let's first take the first case, which is the LL rotation. So we have 40 and we have 30, right? So the balance factor 0, 1, and 2, and this is A, right? This is A. So to apply rotation, with for LNRR rotation, identify A and B and then make A as a child of B. So now we have identified A, and what will be the B? The B will be the child of A. So this is B, right? We will mark the child of A as B, and then it says make A as a child of B. Make A as a child of B. Now this will turn into B. So we will have 40. We will make A as a child. So this will come on the right hand side because it is greater than 40, and 30 will come here. And now if we will calculate the balance factor, so the balance factor of 30 will be 0, the 50 will be 0, and 40 will be 0 also. Now this is an AVL tree. Okay, we have balanced this tree into an AVL tree. So this was the LL case. Okay, for RR it's also very simple. So let's take it the RR case, and we have 60 here and we have 70 here. For RR case, this is A. The balance factor of 70 will be 0. For 60 it's minus 1, and for 50 it's minus 2. So we will make the child and it will be the B, right? We will have to mark B for the child of A, and now we will make 60 as a parent, and we'll make 50 as a child of B. Sorry, 50 will come here because it's smaller, and here we will write 70. And now the balance factor of 50 is 0, 70 is 0, and 60 is also 0. So now we have balanced, and this is an AVL tree. Okay, this is an AVL tree. Now let's look at the case for LR and RL. So we have 50, we have 40, and here we have 45. So this is the case for LR. We have inserted a node on the right hand side of the left subtree, right? On the right hand side of the left subtree. So this will be marked as A. This we'll mark this as B. So now for LR and RR case, for what we will have to do for LR and RL case, identify A, B, and C. We'll have to identify three entities, three nodes. Then make A and B child of C, right? Make A and B child of C. It is also called double rotation. Now, what we will do here, we have identified A, and then the child of A will be identified as a B, and then the child of B will be marked as C. So now we have A, B, and C, three nodes. And then it says make A and B child of C. Now the C is will become the root node. C will become the root node. So now 45 will become the root node, and we will make A and B as a child. So A will come on the right hand side and B will come on the left hand side. Okay. So now this is how we have balanced this unbalanced tree, and the balance factor will be 0 for all. And for the RL case, for the RL case, we have 60. Now we will insert 65. Sorry, uh, something will be lesser, and it will be, let's insert 55. Okay, let's insert 55. So we have inserted a node on the left hand side of right subtree. We have inserted a node on the left hand side of the right subtree, and the balance factor is 0 here, the balance factor is 1 here, and the balance factor is uh, minus 2 here. Okay, so now let's mark them A, B, and C. So this is A, this is B, and this is C, and we will make 55 as a parent, and A and B will be this child. So 60 will come here, and 50 will come here. So now we have balanced this case also. This is LR, and this was RL. This is how we can balance trees. We can balance the unbalanced trees, and we can ensure the time complexity. We can ensure the time complexity of the tree to be log of n, which is why we are doing all these efforts. I hope you must have learned something from this, and if you have any doubt, please watch it again. It's always very helpful when you watch the video again and again. That clears your concept. In the next video, we will use an example, and we will use some more cases of AVL trees, that how on insertion and deletion this the structure of the tree changes, and how all those four rotations we can apply to keep the tree balanced. Thank you for watching.